Today, we're tackling a real mindbender, a true relativistic mystery. Why does the universe itself seem to shrink and warp the faster you go?
So let's just jump right into the big paradox. Picture this. You are on a spaceship. You hit the gas, and you feel this constant, steady push. Logically, right? If you just keep that push going, you should get faster and faster, and eventually you should hit light speed. But you never do. It's impossible. Why? What's the deal?
Well, the whole problem really comes down to a clash between two totally different but equally correct points of view. There's the view from Earth watching your ship, and then there's the view from you inside the ship.
And here's where it gets weird. From Earth, someone watching you sees your ship's acceleration start to, well, slow down as you get closer to light speed. It's like your engine is losing power. But on the ship, you feel nothing different at all. That push against your back feels totally constant, 100% of the time. So, who's right? I mean, they both can't be, can they?
To figure this out, we've got to do what Einstein was so brilliant at. We have to shift our perspective. The real question isn't why the ship can't reach light speed. The real question is, what does the universe even look like from inside that ship?
Right, and this is the absolute core of relativity. When you're inside that ship, you are stationary. You're at rest. You look out the window and you don't see yourself rushing forward. No, you see the Earth, the Sun, the entire galaxy accelerating backwards, away from you. And that leads us to the real head-scratcher. Look, from Earth's point of view, your ship's acceleration slows down because of real physics. Forces just can't transfer instantly. But from your point of view, there's no engine strapped to the Earth pushing it. It's just an apparent acceleration. So with no force holding it back, shouldn't you eventually see the Earth break the light speed barrier?
Now, Einstein's first answer to this is just beautiful, simple logic. Relativity has to be symmetrical. If someone on Earth will never see your ship hit light speed, then it follows that you on the ship can never see the Earth hit light speed either. It's a perfect two-way street.
But that's not really satisfying, is it? I mean, it tells us that it happens, but it doesn't tell us how. If there's no physical force slowing the Earth down from our perspective, something else must be going on. There's a piece of the puzzle that's just missing.
So to find this missing piece, we're going to borrow one of Einstein's famous thought experiments. Let's call it the stamping machine experiment. Okay, the setup is pretty straightforward. We've got our spaceship moving at some ridiculously high speed, let's call it v, and it's flying over a huge, stationary platform. On the ship, there's a machine that can stamp the platform below it, and we've got a super accurate clock. All we're going to do is make two stamps exactly 1 second apart, according to the ship's clock.
All right. Now, from the ship's point of view, this is a piece of cake. The ship is just sitting still, and we see the platform whizzing by underneath us at speed v. 1 second passes, so the platform moves a distance of v. The stamps are v meters apart. Simple.
But now, let's switch things up and stand on the platform. From here, the ship is the one moving like crazy. And because it's moving so fast, we see its clock ticking slower. This is time dilation. So let's just say, for the sake of argument, that for every 1 second that ticks by on the ship, 2 seconds have passed for us down here on the platform.
So here's the kicker. From our perspective on the platform, that ship was flying for 2 whole seconds between making the first stamp and the second one. And if it's going at speed v for 2 seconds, well, the distance between those stamps isn't v, it's 2v. And now we have a serious problem. From the ship, the distance is v. From the platform, the distance is 2v. And the craziest part, both are right. Both measurements are physically real in their own reference frames. So how on earth can the physical distance between two marks be two completely different things at the exact same time?
The answer to this paradox? Well, this is it. This is the missing piece we've been hunting for. It turns out it's not just time that's relative, it's space itself.
The phenomenon is called length contraction. What it means is that as an object moves relative to you, its actual physical length gets shorter in the direction it's moving. The faster it goes, the more it gets squished. So, from the ship's perspective, that entire platform whizzing by underneath is actually compressed. It's shorter than it should be.
And this is just a mind-blowing idea. We all grow up thinking a meter is a meter, right? It's absolute. But relativity just throws that right out the window. It shows us that, just like time, the distance between 2 points is not a fixed thing. It completely depends on how you're moving.
And the most incredible part is that these two effects, time dilation and length contraction, aren't just separate little quirks. You can see it right in our experiment. The slowing of time is what causes the shrinking of space. They are two sides of the very same coin, woven together into the single, fundamental fabric of our universe, space-time.
Okay, so now that we've got this powerful new idea of length contraction in our toolkit, let's go back to our spaceship and finally, once and for all, solve this paradox. So in the old, classical way of thinking, you just expect to see the Earth get faster and faster at a steady rate as it speeds away from you. But in Einstein's universe, something much stranger is happening. As the Earth gains speed relative to you, the very space it's moving through actually starts to shrink from your point of view.
So think about it. Even though the Earth seems to be picking up speed, the amount of distance it actually covers in the next second is less than you'd think, because that distance itself has physically shrunk. The faster the Earth moves, the more space contracts, and the less its speed appears to increase. And that's it. That's what stops it from ever reaching the speed of light from your perspective.
And just like that, we have our complete, totally symmetrical solution. From Earth's perspective, the ship slows its acceleration because of a physical limit on how fast forces can act. And from the ship's perspective, the Earth's acceleration appears to slow down because space itself is contracting. Two totally different explanations for two different viewpoints that both lead to the exact same perfect conclusion.
And really, the big takeaway here is just how incredibly elegant and consistent our universe is. The fundamental laws of physics, like that cosmic speed limit, they don't change just because you're looking at things from a different angle. Relativity makes sure it all just works, no matter who's doing the observing.
It really makes you wonder, though, doesn't it? We used to think that space and time were these rigid, absolute things. Now we know they're flexible, they're relative, so it leaves you with this one last, kind of thrilling question. What other fundamental rules of our reality are just not as solid as they seem?